The interstellar object known as I-Atlas has become the subject of intense research following a recently observed deceleration in its motion. Since its entry into the solar system, ATLAS has been closely monitored through Earth-based telescopes, orbital observatories, and deep space tracking networks. For most of this observation period, it moved in a predictable manner consistent with known interstellar objects, following a path influenced primarily by gravitational forces and the momentum gained long before reaching our system. However, the recorded deceleration introduces an unusual behavior that does not fit easily within expected models. This change does not immediately imply artificial control or deliberate maneuvering, but it presents an intriguing scientific question requiring careful investigation. Researchers are working to interpret the evidence while remaining neutral and grounded in confirmed data rather than speculation. Observation of gradual deceleration. The most striking aspect of the event involving the interstellar object known as ATLAS is the recorded decrease in its velocity. Over the course of approximately 18 hours, Atlas appeared to slow by nearly 8,000 miles per hour. Such a change stands out in the field of celestial dynamics because objects traveling through space typically follow trajectories shaped by inertia, gravity, and occasional natural disturbances. Under normal circumstances, interstellar bodies do not simply slow down in such a steady, continuous manner without a clear, identifiable cause. This makes the observed deceleration both notable and scientifically significant. Natural forces can and do influence the motion of objects traveling through space. Comets, for example, frequently experience changes in trajectory when they pass close enough to a star for their icy components to warm. As these materials vaporize, jets of gas escape into space, sometimes forcing the comet to adjust direction or rotation. This phenomenon, known as outgassing, is well documented. However, outgassing tends to produce sporadic and uneven effects. It can cause wobbling, sudden shifts, unpredictable rotations, and small bursts of speed alterations. What happened with Atlas does not bear these hallmarks. Instead of erratic behavior, the motion change was smooth and consistent across the observed timeframe. This continuous nature of the deceleration suggests that whatever force acted upon Atlas did so in a sustained manner. Considering hypotheses of propulsion. In light of the sustained deceleration, one hypothesis that has naturally arisen is the possibility that ATLAS is employing some form of propulsion. It is essential to clarify that when scientists consider propulsion, they are not immediately implying artificial origin or intelligent control. Propulsion in the broad physical sense refers simply to the application of a force that produces motion. This can come from internal chemical reactions, radiative pressure effects, electromagnetic interactions, or other processes that result in directional acceleration or deceleration. If Atlas were emitting particles, energy, or radiation in a controlled or steady manner, this could generate a force opposite to its direction of travel, causing it to slow down. This would be consistent with the observed smoothness of the deceleration. However, this interpretation requires extreme caution because consistent, long-duration propulsion-like behavior is not typical of known natural interstellar objects. To seriously consider propulsion, scientists must identify additional evidence that supports this interpretation beyond the motion pattern alone. Some observatories reported localized thermal anomalies during the period of slowdown. Such heat signals could indicate a release of energy, which might in turn suggest propulsion-like activity. Yet thermal signatures are not exclusive to propulsion. They can also be created by chemical transitions, by internal crystallization processes, by absorption of solar radiation due to particular surface materials. Understanding the importance of mass and composition. Determining the mass of ATLAS is essential for evaluating the plausibility of various explanations for the deceleration. The amount of energy required to slow an object depends directly on its mass. If Atlas is relatively lightweight, composed of porous rock, ice, or carbon-based compounds, then even moderate natural forces could significantly influence its speed. If, on the other hand, Atlas contains dense metallic structures or compact mineral formations, it could possess a mass many times greater, requiring vastly more energy to create any noticeable deceleration. Current mass estimates are difficult to confirm because they rely heavily on assumptions regarding reflectivity. The brightness of an object in space is not always a reliable indicator of its size or mass. Some objects reflect large amounts of sunlight despite having low mass, while others reflect very little light yet possess considerable weight. If Atlas has a dark, non-reflective surface, it may appear smaller than it truly is. Conversely, if its composition includes reflective, crystalline, or metallic materials, it may appear more substantial than its actual mass would suggest. To refine mass estimates, researchers are analyzing its rotation rate, thermal output, and how light reflects across different regions of its surface. Changes in brightness over time can reveal shape, surface irregularities, and internal distribution of mass. Comparisons to previously observed interstellar objects also provide useful context. For instance, Oumuamua exhibited unexpected acceleration behaviors and showed reflectivity characteristics that challenge traditional models, suggesting that interstellar objects may carry structures or compositions unfamiliar to the solar system. Thermal signatures and spectral data. During the deceleration event, observatories detected heat patterns on Atlas that exceeded the levels expected from passive solar heating. The presence of additional thermal energy suggests that either chemical reactions or physical processes were at work. Spectral analysis also indicated the presence of compounds and particle signatures that do not match the typical composition of comets or asteroids that originate in the solar system. However, the unfamiliarity of these chemical signatures is not inherently surprising. Interstellar objects form in regions with different chemical abundances, radiation levels, and geological histories. The materials present in Atlas could be remnants of environments shaped by conditions distinct from those that form planets and small bodies in our system. The current spectral data show patterns that suggest layered or mixed material compositions, possibly including carbon-rich and silicate components, along with trace elements not commonly observed in local cometary bodies. Researchers are examining whether the recorded heat could result from exothermic reactions triggered by exposure to solar radiation or by internal restructuring of crystalline material. Another possibility is that the object possesses structural features that trap and release heat in ways not yet modeled. Understanding these thermal and spectral characteristics is central to determining whether the deceleration could have been driven by internal energy processes rather than an external or artificial cause. Revising trajectory expectations. Prior to the slowdown, ATLAS was projected to pass through the inner solar system and then continue outward on a trajectory that would eventually carry it back into interstellar space. However, after the deceleration, new trajectory models suggest that ATLAS may remain within the inner solar system for a longer duration. This extended presence has significant implications for research. If Atlas remains accessible for ongoing observation, it allows for a much broader range of measurements, including more detailed imaging, radar mapping, and long-term monitoring of rotational and compositional changes. Scientists are particularly interested in determining whether the deceleration was a singular event or part of a longer sequence of motion adjustments. If Atlas demonstrates additional controlled or steady changes in velocity or direction, this may further inform discussions about the underlying mechanisms involved. Alternatively, if its motion stabilizes and resembles more expected orbital behavior, this could suggest that the deceleration was the result of a temporary process. The longer Atlas remains in observational range, the more opportunities exist to refine mass estimates, identify surface features, track heat signatures, and compare chemical readings across time under varying solar conditions. The scientific community is preparing to use a coordinated observational approach, utilizing ground-based telescopes, orbital observatories, radio and microwave radar systems, and spectroscopic scanners. International cooperation in scientific communication. The unusual behavior exhibited by ATLAS has encouraged increased collaboration among international scientific institutions. Observatories are sharing thermal and spectral data, comparing measurements of brightness and rotation, and coordinating tracking schedules to maintain uninterrupted observation. Scientists from various fields including astrophysics, planetary science, materials science, and deep space navigation are contributing analysis and interpretation. This cooperative approach helps ensure that conclusions are supported by rigorous evidence and evaluated by multiple research perspectives. At the same time, clear communication with the public remains essential. Some individuals have responded to the breaking event with speculative claims of intelligent control. Scientists emphasize that while the event is scientifically significant, no evidence currently supports conclusions about intentional operation. Responsible communication requires acknowledging what is known, what is uncertain, and what future study may reveal. Internal scientific debate and collaborative communication. The study of 3I/ATLAS involves an extensive network of institutions spanning multiple countries, all contributing to the monitoring and analysis of this extraordinary interstellar object. Data, both raw and processed, are shared among teams to facilitate cross-verification and reduce the risk of misinterpretation. This collaborative approach ensures that findings are evaluated using diverse methods and analytical frameworks, strengthening the reliability of conclusions. However, such international collaboration also requires careful coordination and patience. Scientific teams must strike a balance between timely communication and the responsibility to present findings accurately, avoiding premature or exaggerated claims. Public interest in Atlas has surged, particularly because some observed behaviors challenge conventional expectations. Speculation, fueled by incomplete information, can spread quickly outside the scientific community. Researchers have therefore emphasized transparency grounded in documented evidence. For example, the acknowledgement of ATLAS's observed deceleration is not an assertion of artificial origin or intelligent control. It is a neutral statement that the object's motion differs from initial predictions and merits careful study. The scientific method remains the guiding principle. Hypotheses are formed, evidence is gathered, and conclusions are drawn systematically, without presupposing any extraordinary cause. Evaluating known scientific mechanisms. A central focus of ongoing research is determining whether ATLAS's deceleration can be explained by natural processes. One possibility involves thermally driven jets. Some celestial objects emit gas in a preferred direction as surface ices sublimate, producing measurable changes in motion. Another scenario considers internal structures that release material under specific temperature thresholds, resulting in sustained or intermittent outgassing that could alter trajectory. Solar radiation pressure is another factor. Objects with unusual shapes, reflective surfaces, or particular rotational alignments can experience subtle yet measurable forces from sunlight. Computer simulations are actively being developed to test these possibilities. By modeling the combined effects of outgassing, radiation pressure, and solar-wind interactions, scientists aim to determine whether known physics can reproduce the observed deceleration. If simulations confirm that natural forces are sufficient, the behavior can be understood within existing frameworks. If not, researchers may need to refine or expand current models, exploring additional mechanisms that could explain the anomaly. Regardless of the outcome, progress depends on careful, systematic investigation rather than speculation or conjecture. Each piece of evidence contributes to a broader understanding of how interstellar matter interacts with the solar environment. Trajectory revision and extended observational opportunities. The deceleration has prompted a revision of ATLAS's projected path. Originally expected to traverse the inner solar system and quickly return to interstellar space, the object now appears likely to remain within observational range for a longer period. This extended window provides astronomers with an opportunity to gather higher resolution data and study its properties in greater detail. Future observations may include precise surface composition mapping through spectroscopy, thermal imaging to identify areas of active heating, and potentially radar profiling if ATLAS passes close enough to planetary radar systems. Extended monitoring allows researchers to track changes in rotation, brightness, and plasma emissions over time, offering new insights into the internal structure and surface behavior of this interstellar visitor. Each observation not only refines trajectory calculations, but also contributes to models of interstellar object dynamics, helping scientists prepare for future encounters with similar bodies. The continued tracking of ATLAS exemplifies the careful balance of patience, collaboration, and rigorous methodology that characterizes modern astronomy. By systematically observing anomalies, testing natural explanations, and sharing results across the global scientific community, researchers can build a robust understanding of this unique object. Atlas provides a rare opportunity to expand knowledge of interstellar matter, offering lessons not only about its own composition and behavior, but also about the broader physics governing objects that travel between star systems. The meticulous study of its motion, interactions, and evolving properties promises to inform both theoretical models and practical observational strategies for decades to come. Revising trajectory predictions. The deceleration event observed in ATLAS has prompted scientists to update earlier projections of the object's path through the solar system. Prior to the slowdown, its route suggested a relatively brief passage through the inner solar system before continuing outward and eventually returning to interstellar space. However, after motion tracking systems confirmed the gradual reduction in velocity, new trajectory models began to show a different long-term outlook. Atlas now appears likely to remain within the inner solar system for a longer period than originally estimated. There are several possible explanations for this shift, and none of them currently point to a single definitive cause. It is possible that the deceleration was a natural effect resulting from interactions with solar radiation, surface material changes, thermal gradients, or unknown compositional properties. The change could also reflect processes that have yet to be fully characterized in interstellar objects, which may behave differently from familiar comets or asteroids formed in our own planetary system. Regardless of the cause, the most immediate consequence of the slowdown is increased observational access. With Atlas remaining nearby for a longer duration, scientists have an extended opportunity to examine it using a variety of tools. Earth-based telescopes can continue monitoring reflectivity, light curve variations, and structural silhouette changes. Orbital and deep space observatories can analyze its thermal emissions, spectral signatures, and potential particle release events. International collaboration and monitoring. The unusual behavior shown by ATLAS has prompted extensive cooperation across international scientific communities. Research institutions, planetary observatories, and space agencies are pooling observations to build a shared body of reliable data. By comparing measurements from different instruments and geographic regions, scientists are able to refine accuracy and identify consistencies and anomalies more effectively. Teams specializing in astronomy, astrophysics, celestial dynamics, planetary science, and deep space engineering are contributing distinct analytical perspectives. Some researchers are focused on modeling ATLAS's movement and momentum, while others are examining compositional clues from spectral readings. Material scientists are considering what kinds of compounds or surface structures could produce the thermal and reflective characteristics seen so far. Meanwhile, experts in spaceflight dynamics are evaluating how different physical processes could create the measured deceleration. This global cooperation helps prevent misinterpretation by ensuring that observations are reviewed from multiple angles before any major scientific conclusions are presented. Communication among research groups also reduces the risk of isolated data being interpreted out of context. By sharing information openly and consistently, researchers are working to ensure that explanations are grounded in collective evidence rather than speculation. Continuous monitoring efforts are ongoing. Tracking networks continue to record motion, emissions, light signatures, and environmental interactions in real time. As additional data emerges, collaborative analysis will refine or adjust developing theories. This shared research model strengthens both the scientific process and public understanding. Public understanding and responsible communication. The breaking event has naturally attracted public interest, and reactions have ranged from curiosity to dramatic speculation. Some commentators have suggested that the observed behavior indicates intentional navigation or intelligent control. However, scientists emphasize that there is currently no support for claims of artificial origin or purposeful operation. The observed deceleration is unusual, but unusual does not automatically mean intelligent or engineered. Responsible communication is essential in situations like this. Researchers are working to ensure that information is conveyed accurately, clearly, and without exaggeration. The scientific process requires patience, especially when dealing with phenomena that do not yet fit neatly within existing models. Conclusions must follow evidence, not assumptions, hopes, or fears. By presenting data gradually and openly, the scientific community encourages thoughtful engagement. The goal is to help the public understand that discovery often unfolds in stages. Each new measurement contributes to a broader picture that can take time to assemble. Remaining transparent in this process supports trust and prevents misunderstandings that can arise when speculation gets ahead of verified information. Conclusion. The Atlas breaking event represents a notable and scientifically valuable occurrence. The steady deceleration observed challenges familiar expectations about how interstellar objects behave and invites further investigation into possible natural processes or mechanisms that could explain such motion. Whether the behavior of ATLAS ultimately proves to be the result of uncommon natural dynamics, previously unknown compositional properties, or more complex interactions remains uncertain. Continued observation, patient analysis, and open-minded interpretation will be essential. As research progresses, ATLAS may contribute to a deeper understanding of the diversity of objects that travel through our galaxy and the range of processes that shape their movement. The scientific community remains committed to studying Atlas with precision and restraint, recognizing that lasting discovery emerges not from assumption, but from evidence.